In this lecture video, we're going to develop methods for constructing various kinds of confidence intervals for the mean of a population in those situations where the population standard deviation, sigma, is known. Now let x bar be the mean of a random sample from a normal distribution with mean mu and variance sigma squared. Now in this situation, mu is unknown, which is why we want to estimate it with a confidence interval of some type. But we're assuming that sigma squared is known. If the standard deviation is known, then certainly the variance is known. Now, since the random variable given here, this is the standardized version of x bar, since that standardized version of x bar has a standard normal distribution, it follows that the probability that the standardized version of the sample mean being less than or equal to z sub alpha is equal to 1 minus alpha. Now this follows from the definition of z sub alpha along with the complement rule. Now what we can do is we can transform the event specified inside parentheses so that we have a corresponding event or an equivalent event that x bar minus z sub alpha times the standard error of x bar is less than or equal to mu. The probability for that event would be the same as the probability that the standardized version of x bar is less than or equal to z sub alpha, and so that is also equal to 1 minus alpha. So we can think of this either as the probability that the random variable given by x bar minus z sub alpha times the standard error of x bar being less than or equal to the constant mu is equal to 1 minus alpha. Or we could think of it as the probability that the constant mu being greater than or equal to this, random variable. And when we look at this difference, the only part of this that is random is x bar, but once we calculate this thing, the entire quantity obviously becomes random, even though this part over here, these are constants. But we can think of this as the probability that the population mean is greater than or equal to this random quantity, and the probability of that being 1 minus alpha. But when we think of it that way, we do have to keep in the forefront of our mind that mu is not random. Mu is a constant. It's an unknown constant. It's the unknown value of the population mean, and the quantity on the left-hand side of the inequality, x bar minus z sub alpha times the standard error of x bar, that is the random quantity, the random variable in this probability statement. Now, having said that, and knowing now that this probability, the probability of this event being equal to 1 minus alpha, that implies that in repeated sampling, the random variable given by x bar minus z sub alpha times the standard error of x bar would be less than or equal to the mean mu 1 minus alpha times 100% of the time. So when I say that, when I talk about repeated sampling, what I am doing is thinking of this probability in terms of the relative frequency definition of probability, which, as you know, when we think of it, probability in this way, we're thinking of a sequence of events. And so we can think of performing this experiment given on the previous slide, where we select a random sample of size n from this particular normal distribution. For each of those samples, we calculate the sample mean, and then for each of those samples, we calculate this quantity here, x bar minus z sub alpha times the standard error of x bar. So we do that over and over and over again, a large number of times. Now, obviously, we're not going to do that in an experimental situation. In an experimental situation, we're going to do it once, but we can think of this process as being repeated an unbounded number of times. And so when we think of it that way, the probability takes on the relative frequency definition of probability. And so when thought of in that way, what we know is that the percentage of times in that sequence of trials where the population mean is greater than or equal to the resulting quantity here, the resulting random variable, that percentage is 1 minus alpha times 100%. The proportion is obviously 1 minus alpha, but the percentage of the time that would occur is 1 minus alpha times 100%. Now, another way to say this statement here at the top of the page is to say that the mean mu will be greater than or equal to the random variable x bar minus z sub alpha times the standard error of x bar x bar. 1 minus alpha times 100% of the time. So for this reason, we call the random variable given by this expression, x bar minus z sub alpha times the standard error of x bar, we call this a 1 minus alpha times 100% lower confidence limit for mu. Now, as I said, we're only going to, in an experimental situation, we will only select a sample like this once. We'll have one sample. From that one sample, we calculate this lower confidence limit. And once we have done that, the way that we interpret this is that, or the way that we, interpret it and communicate this is we say that we are 1 minus alpha times 100% confident that mu is greater than or equal to this lower confidence limit. Now, next note that the probability that the standardized version of x bar being greater than or equal to negative z sub alpha is 1 minus alpha. And again, we can rearrange the quantities in this relationship here inside the parentheses to get an equivalent event, the event that x bar plus z sub alpha times the standard error of x bar being greater than or equal to mu is 1 minus alpha. Now again, we can read this or think of this probability as being the probability that the population mean mu is less than or equal to this random variable, x bar plus z sub alpha times the standard error of x bar is 1 minus alpha. So this implies that the random variable x bar plus z sub alpha times the standard error of x bar will be greater than or equal to the mean mu 1 minus alpha times 100% of the time. Therefore, the mean mu will be less than or equal to the random variable x bar plus z sub alpha times the standard error of x bar 1 minus alpha times 100% of the time. And so because of this, we call this random variable a 1 minus alpha times 100% upper confidence limit for mu. And so once calculated, we say that we are 1 minus alpha times 100% confident that mu is less than or equal to this upper confidence limit. Now, if we compute both a 1 minus alpha over 2 times 100% lower confidence limit, which is given by this quantity here, x bar minus z sub alpha over 2 times the standard error of x bar, along with a 1 minus alpha over 2 100% times 100% upper confidence limit, which was given by x bar plus z sub alpha over 2 times the standard error of x bar, then using those two confidence limits together, the lower and upper confidence limit, we have a 1 minus alpha times 100% two-sided confidence interval estimate for the mean mu, okay, given by this interval. So the interval from the lower endpoint up to the upper endpoint where we are including the endpoints. And once we have this constructed, we say that we are 1 minus alpha times 100% confident that mu is somewhere in this interval. All right, so to put all these results in one slide, again, we have formulas for lower and upper confidence limits separately, and a two-sided confidence interval that utilizes both a lower and an upper confidence limit. Confidence limits for a single population mean for those situations where the population standard deviation is known. Okay, and so again, the 1 minus alpha times 100% lower confidence limit for mu is x bar minus z sub alpha times the standard error of x bar. The upper confidence limit for mu, the 1 minus alpha times 100% upper confidence limit for mu, is x bar plus z sub alpha times the standard error of x bar. So the only difference between the lower and upper endpoint is you've got, you're subtracting off this quantity here in the lower endpoint, and you're adding it to get the upper confidence limit. For a 1 minus alpha times 100% two-sided confidence interval, we're going to calculate the endpoints x bar minus plus z sub alpha over 2 times the standard error of x bar. So you see what we're doing here is we're starting off at our point estimate of mu, which is x bar, and we're going a distance to the left and to the right to get the limits of the lower and upper endpoints of the confidence interval. And by the way, that value or that distance that we're going to the left and to the right, or another way to say it, the value that we're subtracting from and adding to our point estimate x bar in order to get the lower and upper endpoints, that quantity is called the margin of error of the confidence interval. Now I would just also point out that notice in the notation here for the lower and upper confidence limits, in the subscript for z, we just have alpha. And this is because we're only constructing in each of these two cases a one-sided confidence interval in the sense that we're only limiting either the lower or upper endpoint of that interval. But for the two-sided confidence interval, in the subscript for z, we have alpha over 2. All right, and so we have two endpoints to calculate, and so we're putting half of the alpha beyond the lower endpoint, half of the alpha beyond the upper endpoint, and so that's why we have that. So just make sure that you're aware of this. Now let's look at an example. So suppose that a company, we're getting back to the peanut example. So a company that packages salted peanuts in 8-ounce jars is interested in maintaining control on the amount of peanuts put into jars by one of its machines. Control is defined as averaging 8 ounces per jar and not consistently over or underfilling the jars. Now let me just say parenthetically here, and I may have said this before, but if not, I want to say it now, that we know that there's variability from one jar to the next. There's bound to be, isn't there? It's a production process, and even though it is mechanized, it's part of this, it's the result of these filling machines. We know that the weight of peanuts being dispensed from one jar to another is going to vary. Even though we want 8 ounces to be dispensed in each jar, and that's what the labeling would say, we know that for some jars there's going to be slightly less than 8 ounces, and in other jars there's going to be more than 8 ounces. So when we define the process as being in control or not in control, we cannot speak of the amount of peanuts in any particular jar. What we have to do is think of and speak in terms of a population characteristic, one or more population characteristics for the population of fills of peanuts into jars. And so right now, we're focusing on one population characteristic, the mean fill of peanuts being dispensed into jars, the population average weight of peanuts being dispensed. And so we're defining control in terms of that particular population characteristic, the average weight of peanuts being dispensed. And so anyway, as we go on and look at more ways of performing inferences for characteristics of populations, we may want to expand our definition of what it means for the process to be in control and do this by incorporating additional population characteristics. But for right now, our focus is on the mean weight of peanuts being dispensed. In any given time, we're not going to know exactly. In fact, we will never know exactly what the true value of mu is. And we also need to keep in mind that that may change over time. Obviously, we know that's the case because we have this quality control procedure that is used on a regular basis. And so we know that as the machine goes along and wears and things like that, that things may happen to the machine that cause it to dispense improperly. so for example, get out of control, the mean weight of peanuts being different than 8 ounces. Maybe it's something that has to do with parts wearing out. Maybe it has something to do with the machine being bumped or moved, which could affect the calibration of the machine. And so at any particular time, we're not going to know what mu is. And so what we have to do is rely on a statistical inference. We can't just measure the population mean, because that would require measuring all possible weights of jars of peanuts that could possibly be dispensed at a given time. And so for example, for a given day, that might take a long time to do. And in general, when we think about processes like this, sometimes we even think beyond the product that is produced in a given day. So we're not going to measure mu directly, is what I'm trying to say. What we have to do is select a sample from this conceptual population of jars of peanuts being filled, and then make a statistical inference about that value, about that population mean. And we looked at how to test a hypothesis about that population mean. Now, what we're going to do is use estimation, and in particular confidence interval estimation, to make an analogous type of decision. So to monitor this control, a sample of 16 jars is taken from the line at random time intervals and their contents weighed. The mean weight of peanuts in these 16 jars will be used to test the hypothesis that the mean is indeed working properly. Now, if it is deemed not to be doing so, a costly adjustment will be needed. Now, so suppose that the mean weight of peanuts in 16 randomly selected jars is 7.89 ounces. Suppose also that it's known from past experience that the standard deviation of the weights of peanuts being dispensed is 0.2 ounces. Should the machine be shut down and adjusted or recalibrated? And so to answer this, we're going to do this by constructing the appropriate type of 95% confidence interval that will allow us to answer this question. So we could answer this question by performing a hypothesis test like we did previously, and making a determination based on the data and based on the results of that test to determine whether the machine is in control or not, and therefore whether it should be shut down and recalibrated or not. In this case, we're going to construct a confidence interval to make that determination. Now, since the hypothesis test for this situation was a two-tailed test, the corresponding type of confidence interval is a two-sided confidence interval. And let me just point out, remember at the end of Module 3, we talked about this correspondence, this relationship, this equivalence essentially between hypothesis test and some corresponding type of confidence interval. And so that is what we are taking advantage of in this example. Like I said, we know that we can test that hypothesis and come up with a determination as to whether the machine needs to be shut down. But there is an equivalent, let me put it this way, a corresponding confidence interval that would allow us to make that draw that same conclusion. So because the hypothesis test for this situation, the appropriate kind of hypothesis test is a two-sided or two-tailed hypothesis test, the appropriate type of confidence interval would be a two-sided confidence interval. Now, we're going to perform this or construct a 95% confidence interval. And the reason we're going to do that is because the hypothesis test that we performed was performed at the 0.05 level of significance. The alpha level, the significance level, was 0.05. And so in order to have an equivalent or corresponding confidence interval, the confidence level needs to be 1 minus alpha, where alpha is the significance level of the corresponding hypothesis test. And so because alpha was 0.05, the confidence level for this two-sided confidence interval needs to be 1 minus alpha, or 1 minus 0.05, times 100%. And so that's where we get this 95% confidence level. And so we just apply the formula that we just constructed, all right, x bar minus plus z sub 0.025. This is alpha over 2, isn't it? If alpha is 0.05, alpha over 2 is 0.025. And then times the standard error of x bar. And so we get a confidence interval, a 95% confidence interval, that ranges from 7.792 ounces up to 7.988 ounces. And so now that we have constructed this, we've obtained the sample and we've constructed it, we can say that we are 95% confident that the population mean weight of peanuts being dispensed, mu, at the time that the sample was obtained is somewhere between 7.792 ounces and 7.988 ounces. And when we say that we're 95% confident, what we're communicating is the fact that we are using a process that we know in the long run would produce intervals that contain the true value of the mean 95% of the time. So again, we're thinking of this in the context of relative frequency probability. Remember that there are three types of probabilities. The classical approach, or the classical type of probability, relative frequency probabilities, and subjective probabilities. Well, we are thinking of this in terms of relative frequency probability. In fact, all of what we're going to be doing this semester will, as it pertains to probability, as it pertains to relies on, and then has its interpretation in terms of probability, we're going to be thinking about this in terms of relative frequency probability. And by the way, because of that, that's why these procedures that we are looking at this semester and developing the theory for, and also, you know, those are the kinds of procedures that you've looked at in your other methods classes. That's why those are called frequentist methods, because they rely on the relative frequency type of probability, both in their construction and in their interpretation. So anyway, having said that, so we've constructed the interval. We are 95% confident that the true value of the population mean weight of peanuts being dispensed at the time that the sample is collected is somewhere between 7.792 ounces and 7.988 ounces. And so because of this, notice that the desired value of the population mean, 8 ounces, is not in this 95% confidence interval. And so based on that, or because of that, we're in a situation where we have to make a decision. Is it reasonable to assume that the mean weight of peanuts being dispensed is 8 ounces? Or is there sufficient evidence to conclude that the mean weight is not equal to 8 ounces? And because this set of plausible values for mu, this 95% confidence interval for mu, does not contain the desired value of 8 ounces, we conclude that the mean is not equal to 8 ounces, and therefore that the machine should be shut down and recalibrated. Now let's look at something that we can use for planning an experiment. And what we can do, whenever we're planning an experiment, we're typically going to be testing hypotheses and or constructing confidence intervals in order to estimate the population characteristics of interest. And so what we're doing right now, because we are looking at ways of estimating a population mean via confidence interval estimation, one important aspect of a confidence interval is the width of the interval. And I believe we've talked about width and precision and things like that, the relationship between width and precision. Remember that at a given confidence level, so for example, 95%, we would typically want, well, let me put it this way. Narrower intervals give us more information than wider intervals. Narrower intervals are more precise. They therefore provide more information about the parameter that we're estimating. You'll remember the inverse relationship between the confidence level of a confidence interval and the precision of that interval. As if we increase the confidence level, then the width of the interval gets wider, and therefore the precision decreases. Wider intervals are less precise, narrower intervals are more precise. So at a given fixed sample size, in order to increase the confidence level that we have for the test, we have to decrease the precision. If we want to increase the precision, we have to decrease the confidence. So for example, if we had a given fixed sample size, maybe we've already obtained the sample and we can't obtain any more data values, then in order to, and let's suppose that a 95% confidence interval, while it might be desirable from a confidence level perspective, suppose that it's too wide. Okay, it's not precise enough. Well, if we want more precision, we would have to sacrifice confidence for precision. We would have to decrease the confidence level from, say, 95% to perhaps 90% or maybe 80%. And by doing that, we would narrow the confidence interval, making it more precise. Now, that may not be desirable because we may want to maintain a given level of confidence. So one way that we can try to satisfy both requirements involving confidence level as well as precision is to, before ever constructing the or performing the experiment, determining the sample size necessary to have a certain level of precision at a given level of confidence. And that's what we're looking at here in this slide. So here we are deriving a formula for the sample size required to have a given margin of error and a given level of confidence. And so again, we're in this scenario where we're assuming that the population standard deviation sigma is known. So then the margin of error for a two-sided 1 minus alpha times 100% confidence interval for mu is given by this quantity here. And remember, we called this the margin of error just a while ago. And I'm going to denote the margin of error by E. And then what we want to do is we want to solve this equation for the sample size. And so we're going to square both sides and get n on the side by itself, and just using some basic algebra. And so what we get is this formula for the sample size in terms of the confidence level, which is carried into this equation by the z value, the interval coefficient, in terms of the variability of the population expressed through the population variance, and then also in terms of the desired margin of error. Now, remember that for a two-sided confidence interval, which we're talking about constructing here, the width of the interval is 2 times the margin of error. So we control the width of the interval by controlling the margin of error. And so we have a nice formula here for calculating the required sample size. And so let's look back at our example that we're doing involving peanuts being dispensed into 8-ounce jars. And so the question would be, how large of a sample must be used in order to estimate the mean weight of peanuts being dispensed to within 0.05 ounces at a 95% confidence level? So we want to, what we're wanting to do here is perhaps design our sampling procedure so that we will be able to estimate the mean weight of peanuts being dispensed with a known given precision, in this case 0.05 ounces, while maintaining a desired level of confidence, in this case 95%. And so since the desired level, confidence level is 95%, it follows that alpha over 2 is 0.025. And so, and also the desired margin of error is E equal to 0.05. And so our sample size formula gives us this expression, okay? And so we know that our z value for a 95% confidence interval is 1.96, and we have to be sure to square that. we've been assuming here, and again, this is based on previous information from historical track record of this machine, that the population standard deviation is 0.2, and so the variance of the population would be 0.2 squared. And then the desired margin of error is 0.05, and you can see we have to be sure to square that. And so we plug those values in, and we get a value of 61.5. Now, the sample size must be a whole number. If we were to use 61, the margin of error would not, a requirement that the margin of error be no more than 0.05 would probably not quite be met. And so in order to make sure that that criterion is met, we're always going to take the next larger integer. Now, even if this had given us a sample size value of 61.1, let's say, 61.1, we would not use 61. We would go up to the next larger integer. And so we would use a sample size of 62, and that would therefore give us, if you calculate the margin of error, you're going to see that that does in fact give us a margin of error of no more than 0.05. In fact, if we go back and calculate the margin of error using a sample size of 62, then the margin of error is 0.049784. So that is less than or equal to 0.05. So we've met that criterion. On the other hand, if we had used 61 instead, then the margin of error would be 0.05019. So just a little bit bigger than 0.05. And even though it's not, much bigger, still, we've not satisfied that criteria. So just to be safe, if there's ever a fractional portion on the sample size, we're always going to go up to the next larger integer, regardless of what that fractional value is. And that will guarantee then that we do satisfy that criterion regarding the desired margin of error. All right, so that is how to construct confidence intervals to estimate a population mean. Now, in this set of examples, we've not looked at any examples on how, in constructing one-sided confidence intervals by constructing either a lower confidence limit alone or an upper confidence limit alone. But we will see, I'll provide some examples, some worksheets, problem sets that involve that. You've probably seen that kind of example in your previous methods classes, but just in case you have not, I will provide some examples on constructing one-sided confidence intervals in addition to two-sided confidence intervals. So that's the end of this section on inference procedures for a population mean when we know the population standard deviation. In the next set of lecture videos, we're going to look at inference procedures for performing inferences about a population mean when we don't know the population standard deviation. And that's the more realistic scenario. So we'll start that material in the next lecture video.